Hi everyone, I welcome you all in the next lecture of stoichiometry and process calculation. So, in the previous lecture, I have talked about absorption mass transfer, material balance in absorption mass transfer, and which basically comes under the topic of material balance involving without chemical reaction, right? And we have observed that how much amount of solvent is required to separate a particular gaseous mixture, where gas some of the solute should be there in the gas mixture, and we calculated various parameters like what is outlet gas stream, what is inlet gas flow rate, inlet solvent flow rate, and how to convert mole fraction to mole ratio, and how to calculate the or how we can use the solute free basis concept, right? All of these things we have calculated. So the in today's lecture we'll be talking about I'll be talking about distillation mass transfer, and we'll only see the material balance in distillation mass transfer, right? So this is the last topic of material balance and volume without chemical reaction, right? I tried my best to cover all the mass transfer operation, fundamentals of all the mass transfer operation, where that does not require any mass transfer chemical reaction. Okay, so when we talk about the distillation, I'm not going to write all these definition and all. So basically what happens, you have two components. Let's say I'm talking about the binary component mixture. So let's say you have two liquids, right? And this liquid is there in this flask, okay, having different boiling point. And what happens once you heat this liquid? So I am talking about there are two liquid A and plus B. And if I am talking about boiling point of A is less than boiling point of B, boiling point of A is less than boiling point of, so this should be your boiling point. If boiling point of A is less than boiling point of B, basically what will happen, when A will reach to its boiling point, it will start getting evaporated. And once it will get evaporated, so you will connect this vessel with the system, right? You connect this vessel with the system where there will be a condenser attached to it here. Let's say you have a condenser here, right? And due to this condensation, what will happen, you will collect the more volatile component here, right? So here you will be able to collect the more volatile component eventually. So because A's boiling point is less, and at this point you will start collecting this thing. So just try to understand, at t equals to 0, no product would be there here, right? But as you increase the time, what will happen, when A will reach to its boiling point, the first A will start evaporating, and it will come here, and once it will get condensed, it will come in this distillate. Let's say you have collected. So at early time, what will happen, the mole fraction of more volatile component in the collecting tube, or whatever the vessel that is there for the collection of more volatile component, so mole fraction here will be more, and here mole fraction of less volatile component is less. Is that clear? And with time, what will happen, the mole fraction of more volatile component here will decrease. Why? Because some of the less volatile component will also getting converted into vapor, because it can also reach to its boiling point, right? So this is simple concept of the distillation, where you separate two or more than two components based on their boiling point or relative volatility or vapor pressure, right? So all of these concepts you can study deeply in the mass transfer operation, where you can understand distillation operation very deeply, and I'll be talking these things in the mass transfer operation. But for the fundamental concept here, I'm not going in the deeper. So the ultimate goal is to understand the material balance. So just try to understand. I'll take a simple example of flash distillation here. So in flash distillation, what happens, just try to understand. So there is a heat exchanger, let's say, right? So in this heat exchanger, some fluid should be there that will be exchanging heat between the feed. So now your feed is coming to the heat exchanger, let's say feed, and the feed molar flow rate is kilomole per hour, right? And I am assuming xf is the mole fraction of more volatile component in the feed, right? Now what happens, this feed after passing through heat exchanger, it will be subjected to a pressure reducing valve, right? So it will be subjected to a pressure reducing valve. So this is called as the pressure reducing valve, right? Once this feed is being passed through the pressure reducing valve, so suddenly what is happening, you are reducing the pressure, and in that condition, then due to the reduction in sudden reduction in the pressure, the feed will get flash vaporized, right? And due to this particular reason, it helps you to collect more volatile component and less volatile components separately, right? So once it will come here, so more volatile component will get separated from the top and less volatile component will get separated in the bottom, right? So the top product that we are getting, that is called as the distillate D, and the bottom product that you are getting here, that is called as the residue, right? If I am assuming W kilomole per hour, this thing is there, residue, and D kilomole per hour is distillate. And since YD will be the mole fraction of more volatile component in the distillate, and XW is the mole fraction of more volatile component in the residue. So just now, if we perform the overall balance, first I'll write so I can write F equals to D plus W, right? Now if we do solute balance, that is, let's say our solute is more volatile component, is that clear? That is our more volatile so we can perform the material balance like F into XF, that is equals to D into YD plus W into XW. This is your equation second. Is that clear? So you have two equation, and you will be given either D and W will be given to, and based on the problem you have to calculate something, right? So this is how you perform the solute balance and material balance something. Is that clear? Now next thing that I am coming to the actual distillation unit, and actual distillation unit will also look like that, but the process here, it was in flash distillation, basically you heat the feed, preheating of the feed is there, and then you subject the feed to the pressure reducing valve, and due to reduction in pressure the feed will get flash vaporized, and due to this particular region what will happen, it will get separated into distillate, where you will get more mole fraction of more volatile component, and residue where more mole fraction of less volatile component, that is the vapor and liquid phase, something like that. Okay, so we'll study these things with the help of some one numerical, and then you will be able to understand how these things can be processed, right? So first I'll take one simple example of a continuous distillation column. Let's say column is used to regenerate solvent for use in a solvent extraction unit, right? The column treats 200 kilomole per hour of a feed containing 10% by mole, that is ethyl alcohol, and rest water. So the overhead product is 89% by mole ethyl alcohol, and the bottom product is 0.3% by mole alcohol, right? So you are supposed to calculate what is the daily requirement of makeup alcohol in the solvent extraction unit. So now what is happening here, the overhead is sent to the extraction unit, and the bottom is wasted, right? And then what is daily requirement of makeup alcohol solvent extraction unit, right? It's very important to understand. Just try to understand this thing. So basically what is happening, so you have a distillation unit, and in distillation unit what is happening, so you are sending alcohol and water mixture, right? Alcohol and water mixture is coming here as a feed, and in the feed it is given as it is 200 kilomole per hour, and mole fraction of alcohol here it is given as 10%, right? So 0.10. And after distillation what is happening, you are getting a top product and you are getting a bottom product, right? So top product will be called as distillate and bottom product is called as W, and here this is your YD and here it is your XW. And after that you are sending this overhead product in the extraction unit, right? So this overhead product is coming here in the extraction unit, and then you are extracting something from the alcohol, right? So in this calculation, basically what we see, so ideally let's say if your bottom product would not be there, in that condition what will happen, this amount of W into XW amount of alcohol will not be getting wasted. And ideally in a downstream application of any process industry, you don't want any of your solute or solvent should get wasted, because this will be costly. So you want all of the, let's say if it is not getting wasted, so how much amount of alcohol you would be saving every day, that is good thing. But if it is getting wasted, then you have to send extra amount of alcohol in this extraction unit for extracting the another component. So that is where this concept has been asked in the problem, how much amount of makeup alcohol in the solvent is required, because that much amount of your alcohol is getting wasted from the distillation unit, that should not get wasted. Ideally it should get distilled, and ideally you should get 100% alcohol separation from the top product. It should be 0. W into xw is 0. So by any means, if you are able to calculate w into xw, and then only we can say that much amount of makeup alcohol will be required, because that much amount of alcohol from the distillation unit in the bottom, it is getting wasted. So let's try to understand this thing. So when we talk about the overall balance, so we can write an equation f equals to your d plus w. This is equation first. So your feed flow rate is given as 200, that is equals to d plus w. Now if we perform the alcohol balance, let's say, so we can say f into xf, that is equals to d into yd, d into yd plus w into xw. Okay, so basically our main goal is to calculate w into xw. Okay, but here you have this things is given 89% of ethanol mole fraction is there. So yd is given as 0.89 and xw is also given to you. Xw is 0.3%, right? So we can use this particular formula. So we can have 200 multiplied with 0.10. D is not given to you and yd is given 0.89, plus again w is not given to you and xw is 0.003. Is that clear? So once we calculate this thing, so you will be getting this 20, that is equals to 0.89 d plus 0.003 w. So you have to solve equation first and second. There are two variables and two unknowns and two linear equations. And once you solve these things, you will be getting the value of d, that is equals to 28.87 kilomole per hour, and w you will be getting 178.13 kilomole per hour. So how much alcohol is getting wasted? So amount of wasted, that is equals to w into xw, right? So 178.13 multiplied with 0.003. So here it will be 0.5344 kilomole per hour. So that much amount of alcohol is getting wasted in the bottom product of the distillation unit, and that you don't want it should get wasted, because if that much amount is getting wasted, then you have to supply extra 0.533 kilomole per hour of alcohol in this extraction unit to perform this extraction operation, to separate some amount of solute using this solvent, alcohol as a solvent. So that means and also you have to calculate this parameter in daily basis, right? So you have to calculate the makeup alcohol required per day, that is equals to 0.533, that was in kilomole per hour. So you have to multiply it with 24, right? So this will be your these things on the daily basis, right? So once you do this calculation, you will get the answer, and that will be in your kilomole. And sometimes they can ask you in kg also. So you have to calculate ethanol, what is the molecular weight of ethanol, that is equals to I think 46 gram per mole, right? So you have to multiply this with the 46 gram per mole as well, and then you can convert this into kg as well. So it depends in which unit they are asking, kg per day basis or kilomole per day basis, something like that. Okay, so this is how you perform the material balance using your distillation operation, and then downstream process was your extraction. So in the next lecture I will be talking about some problem which is also based on material balance involving without chemical reaction, and there I will be talking about there is a absorption unit, and from the absorption unit some amount of liquid that you are getting in the bottom product, and then that particular liquid will be used in the distillation column, and will perform the distillation operation, and will calculate some another parameter that is being asked in the problem. So till now I have not seen any kind of question that has been asked in the GATE or BARC in any other exam where they have used two unit operation together, like absorption or distillation or extraction or distillation or absorption and extraction, something like that. These kind of questions will be solving in the next lecture. Okay, thank you.